So finally, let's switch gears to the third type of carbonyl condensation reaction that we mentioned earlier. In this case, the enolate is not attacking a carbonyl. The enolate is attacking the beta carbon of an alpha-beta unsaturated carbonyl compound. So remember, that's called a conjugate addition, or also known as a 1,4 addition, that occurs when we have some sort of nucleophile adding to this alpha-beta unsaturated compound. It's also called an enone, right? Ene for the double bond, one for the ketone. That makes sense. So when you hear me referring to an enone, that's an alpha-beta unsaturated carbonyl compound like this. We saw this happen before in the ketones and aldehydes chapter, where if we have this enone here, some sort of nucleophile attacks the beta carbon, okay? The electrons move on to the alpha carbon, making this enolate, which, remember, has a resonance structure, CO minus, double bond, C, and then the nucleophile there added to the beta carbon. Then a proton transfer will protonate the enolate and deprotonate the nucleophile that had been added, giving us the neutral conjugate addition product. Notice that the double bond is gone in the conjugate addition product. Essentially what's happened, if you can envision it this way, is that the nucleophile and H add across the double bond of the enone. An alternate way of looking at it, although it has a couple more steps to it, but for some students it's a little more logical. Rather than just having these electrons land on that carbon there, what you can do is attack the beta carbon, have the double bond migrate to the alpha beta position, and kick electrons up to the O minus. That gets us directly to the enolate resonance structure with the O minus, but they're really identical. I think actually this is probably a little more correct, that the O minus accepts a good amount of that electron density, but it's probably going to be a little faster and a little easier for us at this point to just imagine those double bond electrons just landing on the alpha carbon, because then it's really easy to see how it gets protonated. Down here, if you tried to protonate the O minus, you would have an enol, which of course tautomerizes to the keto form, but that's a lot of extra steps to be thinking about, especially if you're pressed for time. So for a conjugate addition, just have the nucleophile add to the beta carbon, have the electrons go on to the alpha carbon, and then protonate. Right? That's it. Or do a proton transfer if that's necessary. Right? So if we have a stabilized enolate, that can act as a nucleophile in a conjugate addition. That's called the Michael reaction. So here's ethyl acetoacetate. It's a beta keto ester. It can make a stabilized nucleophile on the alpha carbon that's between the two carbonyls. So I'll just abbreviate and make that the enolate, just like that. Okay. The enolate will add to the beta carbon of this alpha-beta unsaturated carbonyl compound. This is 3-butene, 2-one, right? So CC double bond, then C double bond OCH3. So we have alpha, beta. The enolate from acetoacetate here adds to the beta carbon. Then remember what I said we can do. We can just put those electrons right on the alpha. What we get just from doing this direct addition is C double bond O. The alpha carbon of the enolate here still has that ester group, right? Attached C double bond O, ETO, still has an H attached. The new carbon-carbon bond forms between the alpha carbon of the enolate and the beta carbon of the enone. So, get that. Our intermediate here has just one H still on that alpha carbon, and that's where the minus landed. then, in our second step, protonation of that enolate gives us our product. So one of these H's was added right there. Okay, so enolate attacked the beta carbon, pushed electrons onto the alpha, so that gave us this new enolate as a product. So hydronium protonates that. Our product is a 1, 2, 3, 4, 5. It's a 1,5 dicarbonyl with an extra ester group on carbon 2. Now, if we like, that ester group, right, that's an ester group that's on an alpha carbon next to a carbonyl. Okay? If we want to take this further, we could do heat and hydronium to decarboxylate, just like we've done always when we have that ester group alpha to a carbonyl. So if we did that, we could end up with a regular 1,5 dicarbonyl. Okay. So be looking for this characteristic functional group, having two carbonyls that are 1,5 to each other. That can come from having a temporary ester group attached to the second carbon of that 5-carbon sequence. The retrosynthetic disconnection there is between carbon 2 and 3. So essentially between alpha and beta to the original carbonyl. Right there. So here's how the textbook drew that mechanism, exactly the same as we did. Enolate attacks beta of the alpha-beta unsaturated compound. Gets protonated then. We have a 1,5 dicarbonyl with our ester group on carbon 2, which can optionally be removed by heating it to decarboxylate. So for the Michael reaction, we have Michael donors and Michael acceptors. And the Michael donors are always going to be compounds that can make stable enolates. Okay? So in other words, a beta diketone, for instance, where we can have a stabilized minus charge on the alpha carbon in between them. Right? Beta ketoester, same thing. Diethyl malonate, that's the diester, the same thing we used in the malonic ester synthesis. Beta ketonitrile will work. The nitrile, the C triple bond N, reacts similarly to a carbonyl group. We'll see that over here. Same thing with the nitro group. We can sort of write carbonyl analogs, meaning functional groups that perform the same function as a carbonyl, at least in these reactions. So here's our carbonyl. That can behave similarly to a nitrile, C triple bond N, similar to a nitro compound, right? So that's N double bond O, then single bond O minus, and the N has a plus. So the nitro looks an awful lot like a carbonyl. It looks like a carboxylate, sort of. So C double bond O, N double bond O. The nitrile is C triple bond N, but it's the same oxidation state as, say, a carboxylic acid or an ester would be, and it's carbon attached to an electronegative atom. So this nitrile is very similar to the ester that's up here, for instance. Okay, so all of these Michael donors, the compounds that make the enolates, have to be stabilized enolates, and all of these are stabilized by those extra resonance structures. The Michael acceptors, look at what's in common between all of these. If we have a molecule that's a Michael acceptor, these are all unhindered at the beta position. right? So propenal has CH2 double bond CH, C double bond O, right? 3-butene-2-one, CH2 double bond CH, C double bond O, CH3. So all of these have a CH2 on the beta carbon. Okay? No extra R groups on that beta carbon. So those are the ones that will react the most favorably to a Michael reaction. That's not to say that it's impossible to have an R group on that if I did this compound, right? This is 1, 2, 3, 4, 5. 1, 2, 3 pentene 2-one. Okay? It just has a methyl group on the beta carbon. That's probably okay. It will react much more slowly than these unhindered ones will, but you can probably still get it to react, especially if the product is favorable. So be able to identify, and look over here, propene nitrile, okay? CH2 double bond CH, C triple bond N. So where the carbonyl would be instead as a nitrile, here's nitroethylene, CH2 double bond CH, NO2. Right? Remember we said the nitro group is like a carbonyl analog for this function anyway.